Hey FRM guys, once again a video, and now we're going to talk about copulas. Okay, so in this video I'm going just to introduce. I'm not going to talk about too much, but I'm going to give you an example of a copula, so maybe it will give you a better feeling why is it important in risk. Okay, so if we have, for example, two stocks, X and Y, right? We saw the situation before that we know that these are, let's assume that the returns are normally distributed. Okay. And to simplify the discussion, let's assume that X and Y are normally distributed with the standard, with a standard normal distribution. I mean, it's an unrealistic assumption, but I think it will actually give you a very good hint of what's, of why we need copulas. Now, the question that we ask, right, is how those two guys behave together. Okay? What we want to do, we want to model them together. Okay? So the fact that they have each one a marginal distribution which is normal standard, doesn't guarantee to us, right, what will be their joint behavior. Okay? So for example, if we want to think about, say, Gaussian copulas, right, we assume that their joint distribution, how they behave together, is going to be basically given by some covariance matrix. Say C1, so it's going to be 1, 1 because they're normally distributed, right? And here it's going to be some rho. And you will see immediately that in this case, rho will be the correlation, right? Now, this covariance matrix, right, can be, can actually have, any rho, and which still will be, and those two guys will be normally distributed. Each one separately will be normally distributed with a standard distribution. Let me show you how you can construct it, right? So you have X, which is normally distributed. Say you have Z, which is also normally distributed, but then the correlation between Z and X is 0. Now define a new variable Y. Okay? This Y is going to be the following. It's rho times X. So I take rho, I multiply by X plus square root of 1 minus rho square times Y. Times Z, sorry. Times Z. Okay? And then, how X and Y are going to be jointly distributed? Let's see. So first of all, let's persuade ourselves that Y itself is actually standard normal. Well, because X and Z have the expected value of 0, this is going to be, because their sum is going to have an expected value of 0. What is going to be the standard deviation of Y? What is going to be sigma Y? Or variance of Y, right? So this is going to be variance of rho times X plus square root of 1 minus rho square times Z, okay, which is going to be basically rho square times variance of X plus square root of 1 minus rho square times variance of Z plus rho square root of rho plus rho times square root of 1 minus rho square, 2 times of this guy, right, times covariance of X and Z. But because covariance of X and Z is 0, what you're going to get rho square times variance of X, which is 1, right? So we can say that this is 1, sorry. Plus square root of 1 minus 1 rho square to the square is just 1 minus rho square times 1, because the variance of Z is 1, right? And now when you cancel those two, you're getting that this is 1. Right? So y is actually normally distributed with a variance of y, 1, and expected value of 0, so it's actually distributed as a standard normal. Right? Now, what about the correlation or the covariance between x and y? Right? So this is once again easy peasy. It's going to be rho times the covariance of xy, of xz, of xx, sorry, plus square root of whatever, 1 minus rho square times covariance of zx. And this is 0, right? Because that's how we said. And this is 1. So we are saying that the covariance of xy is rho, right? Now, because x and y are standard normals, right? The covariance of x and y equals to basically the correlation of x and y. Why is that? Because this is going to be just the covariance of xy divided by the variance of x, sigma divided by sigma x times sigma y. Both of them are 1, so it's going to be covariance of xy. Right? So for standard distributions, and only for standard distributions, right, the covariance of xy equals to the correlation of xy. So what do we get here? This is an example, right? Why do we need like all these copulas? Okay, you have two stocks with two different, with the same marginal distribution, right? Both of them are standard normal, yet their behavior is going to be very different depending on their correlation, right? Their joint distribution is going to be your, the most elementary example of a copula. It is going to be a Gaussian copula. And be surprised, right, that in many cases, it's actually enough. You don't need to go to much more fancy models when you want to, actually estimate structured products. And we will do an exercise in class where we are going to see how you can use this kind of modeling in order to start, estimating your risk of how does the risk work for structured products. Okay, for synthetic structured products that were the main culprits of the, of the crisis that occurred in '08. All right, so I'm going to talk about this in class, but you just need to keep this toy example in mind. Thank you very much and have a great day.